In this video, we're going to talk about a real-life example where we're going to use gravitational force and acceleration and velocities to determine height, speed, and falling position of a falling object that is in a projectile motion. If v of t represents the velocity of an object, then the acceleration of an object is given by a of t, where the velocity is the derivative of acceleration and position is the second derivative of acceleration. So if you're given the acceleration formula to get velocity, you take the derivative once, and to get position, you take the derivative twice. Now we're going to talk about what's called free fall constants. It has been shown through experiments that the acceleration due to gravity near the surface of Earth is 32 feet per second squared, or 9.8 meters per second squared. Using some calculus, you can get that the position formula is 16t squared, or 4.9 t squared, depending on what units you're using. These are two equations that you're going to have to memorize. Example 3. A dynamite blast propels a rock straight up with an initial velocity of 160 feet per second. It reaches a height of s equals 160t minus 16t squared feet after t seconds. So using all of this, we're going to determine these four things. How high does the rock go? What is the velocity and speed when it is at 256 feet above the ground on the way up? And what is the velocity and speed on the way down? What is the acceleration at any time t during its flight? And when does the rock hit the ground? Before we do these four things, we're going to go ahead and look at a graph of what's going on. So here I have a rock, and I'm going to go ahead and launch it. So as this thing goes up, it's going to go up, it's going to lose some speed, it's going to level off, and then it's going to gain speed as it falls back towards the earth. So we have a rock, and as it moves up, it starts to slow down and lose speed. And then as it goes down, it gains speed again. Now I'm going to run this animation one more time, but I want you to pay attention to the velocity and speed. And so if we notice, speed is just the absolute value of velocity. So when the rock is going up, the speed and velocity are the same. When the rock starts to go down, the speed and velocity are opposites. So the first problem says, how high does the rock go? So in order to better observe this, I'm going to go ahead and put a graph on the screen. And this maps the projectile motion. And so what we want is we want to find when it has a highest point. Well, where it has the highest point, we have that the tangent line is horizontal. So at the highest point on this graph, the rock stops moving for a second, and so its velocity becomes 0. So the rock goes up, and then it stops, and then it comes back down. So the rock stops when v of t, which is equal to the derivative of position, is equal to 0. So we're going to use that to find the t value of where this rock stops moving. So we have that our position formula, s of t, is equal to 160t minus 16t squared. So the derivative of position is 160 minus 32t. And then we set that equal to 0 because remember this is equal to velocity. And we want the velocity to be 0 because when you throw something up in the air, its speed stops for a minute right before it starts coming back down. And so now we just solve this. And so now we know the time at which this thing gained a maximum height. So in order to find the maximum height, we're going to take that t value and we're going to go ahead and plug it into our position function. So we have S of 5 is equal to 160 times 5 minus 16 times 5 squared. And so we have the maximum height of the rock is 400 feet. For part B, we want to know what is the velocity and speed when it's 256 feet above the ground. So the first thing we need to do is find out the t value when it is 256 feet above the ground. So we have our position function is equal to 160t minus 16t squared. And so we're going to set that equal to 256. And then we're going to go ahead and solve for t. So I get t is equal to 2 and t is equal to 8. And so these two t values represent the times for when the rock is 256 feet above the ground. Now what we need to do is we need to figure out the velocity. Well, we know v of t is equal to s prime of t. And we already know the derivative is 160 minus 32t. And so we just need to find v of 2. So we just plug 2 into our velocity formula. And we get this is 96 feet per second because it's velocity. And then we need v of 8, which is going to be the same formula, but you're just going to plug in 8, and you end up getting 96 feet per second. So this one represents the velocity going up, and this represents the velocity going down. And now what we need to do is find the speed. So speed is equal to the absolute value of velocity. So the speed at t equals 2 is just the absolute value of 96, which is 96 feet per second. And that was the going up. Now we want the one that's going down. So the absolute value of negative 96 is positive 96 feet per second. So the speed is 96 feet per second, both going up and going down, but the velocity is negative when it's going down and positive when we're going up. Now part C wants us to find the acceleration. And to find acceleration, all we have to do is take the derivative of velocity. So acceleration is equal to the derivative of velocity. And we know our velocity function is 160 minus 32t. So v prime of t is just equal to negative 32. And this is our acceleration. And so when we do acceleration, it's given in feet per second squared. Each time we take the derivative, we're doing it with respect to time. So we're always going to get another second. And so a second times a second is second squared. All right, and the last part, part D, is asking us to find when the rock hits the ground. So we want to know when our position is 0. It's 0 when we launch, and it's 0 when we hit the ground. Because if we look at this graph, right there is 0, and right here is 0. Those are our y values. So S of t is equal to 160t minus 16t squared. And so we set that equal to 0, and then just solve. And so we get t is equal to 0 and t is equal to 10. And so t equals 0 represents when the rock was launched, and t equals 10 represents when the rock landed.